This lecture is honestly probably my absolute most favorite in mechanics and materials because it is like all math. So if you're super duper into math, it's great. And even if you're not, it's still important to know where these equations are coming from because that's what makes you a good engineer, is knowing what assumptions went into stuff and being able to think through and the processes and all that kind of stuff. So anyway, I'm super excited about this lecture. Okay, so plane stress transformations. Okay, so in theory, this is what we have, is we have like this like particle or this element, and it's got all these like normal stresses and all these shear stresses and all this kind of stuff, and it looks really confusing. So like whenever you're doing these problems, you kind of get like freaked out and you're like, why are all these arrows pointing everywhere? People can't possibly do this in real life. And the answer is they don't. In real life, most loadings are coplanar unless you're doing something super fun. But for the most part, a lot of what you're doing is just going to be coplanar, and so we can analyze it in a single plane, which is why we call it plane stress. Okay, so for example, we might have a problem where all we have are like the x's and the y's. So like all of these things here would be gone, and so you could redraw it in a way that just shows the x and the y. So basically, that's what we're going to be looking at. Now, the next step that we're going to do is, the idea is that maybe we can like rotate this block such that to get to this like sweet spot where we can kind of get rid of extra kinds of things, or, you know, just basically the idea is like what happens whenever we rotate these around. And so right now we're just going to do like a ton of math and geometry. It's going to be amazing. But the idea is that we're eventually going to ask the question, like, is there like this perfect angle at which we can, you know, rotate it at? Because like if I kind of rotate it this way, then like the omega is still like pointing that direction. You know, these are still going this way, and these are still going this way, but like maybe there's a way that I can get like this one to combine with this one geometrically so it sticks out. Well, probably not that direction. Like what if I can get this one and this one to combine so it sticks out this way, and you know, these, hold on, these two are the other ones, you know. So the idea is like, can I make like these special, like if I just angle it just right, can like, yeah, like this and this, can they combine to make that? And can this, and I think it would have been this one over here, combine to make that, and this combine to make that. So that's kind of what we're going with, is that's the ultimate goal. But right now we just need to know, like, as I'm rotating this point, you know, how do these respond? And because in real life, it's not like everything is made of like little block particles, right? We've just turned them into blocks to make them easier to think about. So it really doesn't matter if we do uppy-downy blocks or side-to-sidey blocks or angly blocks or any kind of shape blocks, because they're not even really blocks. We could make them all spheres or, you know, I don't know, dodecahedrons, but it just makes more sense or a little bit easier to think about them in cubes. I keep saying squares, clearly they're cubes. But anyway, so that's kind of what we're going to do, is what happens as we rotate these. Okay, so first of all, I should never, ever be in charge of drawing straight lines. Okay, that said, let's continue. Okay, so now I'm going to use, so if before, you know, this was my x and my, you can't see that, my x and my y axis, which makes sense. I'm now going to, as I rotate this, I'm going to call this up here my y prime axis and my x prime axis. Y prime and my x prime axis. Okay, so right now what we're going to examine is we're just going to examine the stress of what these, of what they look like. Okay, so now still along the uppy-downy, so these forces themselves aren't moving. This force is still right here, and this tau xy is still right there. And the sigma x is still right here, and the sigma y is still right here. Okay, so these are still on these locations. Okay, we're just playing. Okay, and let's say that I have rotated this an angle theta. Okay, so I'm on my new axis. I should actually have drawn those in a different color. So I've got my new axis here, my x prime and my y prime. Okay, now that we have stress, I'm going to draw the same picture, but I'm going to look at this, well, not exactly the same picture, but I want to look at the surface area now. So take a look at this triangle here. Okay, and honestly, we could look at any of the triangles. I just like that one. So I'm going to look at this triangle here, and so it's going to look like, do surface area. Woohoo, surface area. This is geometry and algebra and all kinds of fun stuff. Okay, so now I'm going to look at this triangle here, to dupe and to dupe. So this angle right here, so there's a couple of ways. A lot of students, it drives me crazy. I don't know how y'all do it. You just go, well, clearly this is also theta. And I'm like, but how do you know? So if you need to know how, it's theta because this is theta and this is 90. So this is 90 minus theta. And since this is 90, then this is 90 minus theta, which makes it theta. Okay, so if that was helpful. Otherwise, you're just like, well, duh, why are you telling this stuff we already know? So this angle up here is going to be theta. I still got my right angle hanging out there. Okay. So if, this is a fun, so remember that this is a thing that exists in 3D. Okay, so if the surface area of that is delta A, so let's try this again. Surface area, so we're going to call that delta A. Now we can still, just like the lengths of a triangle, we can use trigonometry. We could do the same thing with the surface area because it's just all proportional. So that means the opposite sign from the theta, then that means the surface area on the bottom is going to be delta A sine theta, and the surface area on the left is going to be delta A cosine theta. Okay, so now that we know what the stress is on each face and what the forces are on each face, then and the stresses and the surface area, then that means that we can actually come up with the forces on each face. So remembering that force is going to be that pressure times that surface area, then what we're able to do is say, okay, well then this sigma here, stress here is going to turn into stress times the surface area. So this value becomes sigma 1, let me change my pen a little bit. So that's going to become sigma 1 delta A cosine theta. And I know that some of you are thinking, well, don't you technically need to know like what proportion of this is going to be blah, 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 because blah, 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 blah. And there's a couple of answers, and the easiest one is no, because that proportion blah, blah, blah has been captured here. Another reason that we're not like worrying about like divided by 2 is because remember this is like a super, super, super small dimensionless thing anyway. So all of this is theoretical, and at some point we're going to say, and then the math says, and then continue. So we do still have that. We're going to have the same thing on the bottom with sigma y, that was supposed to be sigma x, sigma y delta A sine theta. Okay, and then we have the shear stress, and the shear stress is going to be turned into a force. So it's going to be tau xy times delta A sine theta. And then this one over here is going to be tau xy delta A cosine theta. Okay, so what we don't have right now is an object in equilibrium because we're kind of ignoring the fact that up here we're going to have forces as well. So this force is going to be some new unknown sigma times the delta area. And then there's also going to be some unknown tau x prime y prime times the delta area, because we don't know what those are going to be. So now that it's kind of broken off, we're just using, these would be like, I guess, internal forces of our little cube, even though, it doesn't really have it because it doesn't exist. Anyway, but we're just trying to get the theoretical stuff down. So basically, in order for this to be in equilibrium, you would have to have these equivalent forces here. And so both of these thetas are right there. Okay, now we get to do the math. Okay, so we are going to do the sum of the forces in the x and the y directions. So let's go nuts. Let's solve these. We've got that the sum of the forces in the x direction, okay, and this is back to my x, y thingy. So I've got, this is going to be fun. All right, I've got negative sigma x delta a cosine theta. So I have this one, and then like a part of this one and a part of this one. All right, and then I have minus tau x y delta a sine theta. Okay, and then I'm going to move these over here so you can see what I'm doing. All right, now I'm going to take the parts of this one that go lefty-righty. So that would be minus again. Yeah, lots of minuses. Minus tau x prime y prime delta a. But since it's opposite of the theta, then that's going to be times sine of theta. Woohoo! Don't want to mess something up here. And then for this one here, I'm going to do, that's actually plus, and it's going to be with a cosine. So sigma x prime delta a cosine theta. And all that's going to equal 0. Woohoo! Okay, so now I'm going to do the same thing. But again, I'm going to do it in the y direction. All right, so I've got the sum of the forces in the y. Okay, I've got negative y delta a sine theta, and then minus tau xy delta a cosine theta. And then it's actually pointing up, so the tau x prime y prime times the cosine, because it's adjacent of theta, is going to be positive. And actually, so is the other one. So we're going to have two positives here. So positive sigma x prime delta a, but this is going to be sine theta. Okay, so these are the two equations now that are enforcing static equilibrium on this problem. And again, it's because the piece of material, the metal, whatever it is that we're looking at, doesn't move. Now, as much as I desperately want to solve these for each other, so basically what our goal is to get a sigma x prime and a tau x prime y prime. And so even though we have a ton of variables, the only two so-called unknowns are the tau x prime y prime and the sigma x prime. Okay, so if you were going to solve that with two equations and two unknowns, then you end up with this equation here. So there you go. Now, if that doesn't get your heart racing, I can't imagine what would. Yeah, I'm sorry. This is as exciting as it gets. And this is where I kind of got to go, but wait, there's more. So I just kind of labeled this sigma x prime, and you just said like, oh, okay, whatevs. But there's no reason that I couldn't have labeled it sigma y prime, and or in general done this on any of these surfaces. So there's a couple of ways that you can kind of picture it, but essentially, if we were going to rotate this and do a sigma y prime, what we can do is, instead of having to do all this math again, we could let go over to theta plus 90. So we're basically just going to rotate everything by 90 degrees. Or if we use some of our trigonometric functions and our stuff that we learned in, well, trigonometry, if you kind of plug that in and you play around with it, it just flips a couple of signs. So what you want to look at here is how these are just a little bit different. So the x and the y are essentially the same, except this one has a negative sign here and it has a negative sign here. So other than that, they're exactly the same. So this way, if you were going to rotate the block, so back to what we were doing to begin with, is we were rotating our block, and we wanted to know, okay, what is the sigma x prime, the sigma y prime, and then the tau x prime y prime. So those would be over here. So tau x prime y prime x prime, y prime, and again, the opposites over there that match. So basically, we do all of that so that we can say, well, holy Gertrude, where did all this go? I'll go find it and bring it. Okay, hopefully this picture helps. So basically what we've done is I've said I can take this picture here and I can turn it into this picture. If I want to rotate that block for some reason, I can rotate the block. And when I rotate the block by this angle theta, and I use these equations, now it looks like it's an alligator eating this tennis ball. Anyway, alligator eating the tennis ball is what makes those things the same. So the idea is, how do I convert? If I was going to kind of angle that block, how does it affect my calculations? And the answer is, it affects it like this. So hopefully that satisfies your curiosity. Yay!